Okay, hello. This is the theory for chapter 9, which is impulse and momentum. So, um, impulse and momentum is relating force, velocity, and time, right? What we did before in chapter 7 and 8, we were relating force, velocity, and distance, because remember, energy is Newton meters. That's what a joule is. So now we're going to be relating force, velocity, and time, which is what momentum is. So we have um, ADS is equal to VdV starting out, right? And we know that we have that F equals MA. And if we were to rearrange this A, we replace A here with dv dt. So dv ds dt is equal to v dv. So as you can see, the so the ds dv is what we used for energy. So now we're going to use the fact that A is equal to dv dt for impulse and momentum. So we get F is equal to mdv dt. So F dt is equal to mdv. And when we integrate this, we get that F dt, we're going to leave this side unintegrated for now, right? But F dt from time 1 to time 2 is equal to mv2 minus mv1, right? And this equation here, if I add on an integral to it right here, right, this equation is the principle of impulse and linear momentum. Because this is what momentum is. Momentum is mass times velocity, right? So nothing crazy about that. And this is a vector equation, the force and the velocities, these are vectors, right? So if we look at the formula sheet, we're here, we have principle of linear impulse and momentum. As you can see, they took the mv1 and they put it on this side. So mv1 plus this integral of force dt is equal to mv2. And there's also this for rigid bodies, but it's the same thing, just your velocity is whatever sub g means. So that's all there is for it. We give this a variable. For impulse is I. I is equal to impulse. So I is equal to the integral of f dt, which is equal to mv2 minus mv1. So there is a few things we need to elaborate here for this unit, right? So time is important, obviously, for momentum. Momentum cares about the time. Like last chapter and the chapter before that, for work and energy, we didn't care about time. Like it could take however long, the energy in the equation would not change, right? So time dependent. So linear momentum, which we call L, it's L bar because it's a vector, is equal to mv bar, right? So this would be like saying L2 minus L1, right, in this scenario, if the masses were different. If not, then it would just be m and then factored out v2 minus v1. So L is equal to mv. So momentum and velocity will be in the same direction. So if we have our momentum going this way, our velocity travels along the same path like so, right? So this is linear momentum. And linear impulse is just the integral f dt right here. This is also both vectors, right? So I is equal to integral f dt. And if force is constant, it's just going to be I is equal to F delta t, right? So that's if force is constant. But if it's a function of time, then you use this integral, right? We also have, graphically, we can find impulse on graphs for F versus t graph. If we have some shape like this, and we have this section here, t1 and t2, the area is equal to this integral, right? This is the integral of this area here. And this would like extend all the way down, of course. That's how that works, right? So this area corresponds to this integral. So that's how you can look at it graphically. So if you get a graph question and it asks what's the impulse, and it gives you an FT graph, you know to find the area under the curve, which will give you your answer, right? So let's think about here this equation, which is this one. So I'm going to rewrite it as I is equal to mv2 minus mv1. Now, can you split this into your components? Well, yes, you can split this into x, y, and z components, right? So that is, yeah. So you can get like a mv2x minus mv1x is equal to ix, right? And same thing if you bring in this integral, you can split your force into x, y, z. So everything here can be split into components. So the reason for there being a sum here, by the way, is because it's like all the forces that are acting on the particle. So not just like the one little bit. And so the way to read this equation is momentum 1 plus impulse of all forces is equal to momentum 2, right? That is how you'd want to read this equation, and this equation as well. So, yeah. Anyways, we need to talk about how we use these. How we use momentum in questions. And so now we're going to be looking at something called conservation of momentum, right? And this is just saying that if we have no external forces, right? And we have, so there are a few scenarios here for conservation of momentum. So scenario 1 is two bodies collide. Scenario 2 is two bodies collide and stick together. This is two bodies collide and both both have a reaction, right? So both both react. And then scenario 3 is two bodies collide, one reacts, right? So those are our three scenarios where we have conservation of momentum. So for scenario 1, which is right, we're gonna have, so we have m1 v1, so we have one body, and how conservation of momentum works is that the momentum at the beginning is equal to the momentum at the end. So the sum of all the momentums initially is equal to the sum of all momentums at the end. So since mass is constant, that means that the velocities would be adding up. But anyways, we have two bodies, right? So m1 v1 plus m2 v2 is equal to m1 v1, and this should be, I'm going to call this v prime 1 because it's a new velocity. Some people would put like a subscript. They go like v11 v12 and then v21 v22. So that's just however you want to write it. It means the same thing. And then m2 v prime 2. Don't confuse the prime with a derivative in this case. So, yeah. So, this is what happens to our equation. No external forces, by the way, right? There's also, so this happens when they collide, and then there's a reaction after that. So this is when they both split off into, like for example, if we have ball 1 and ball 2, and then they hit each other. So this is their path. They hit each other, and then ball 1 goes this way, and ball 2 goes this way, right? They both have a velocity after, so yeah. And then another situation, so scenario 2, two bodies collide and stick together. So we have this ball and this ball. They collide, and they form this new system where they stick together and go off this way. Go off this way or something, right? Yeah. So that's scenario 2, where for this we'd have m1 v1 plus m2 v2 is equal to m12 v12, right? So this is saying the mass of the two things are connected now, so that means their velocity is connected as well. So you'd solve for whatever. And remember, this can be split into components. As you can see, these are off at angles, which means they have x and y components for their velocity and their momentum, right? And then finally, scenario 3, we can imagine that we have a wall and we have a ball, right? Or we could say this is like a piston thingy, so that it actually has an initial. It goes like this, it goes like this. So the piston doesn't get any movement afterwards, and the ball goes off this way, right? So that gives us m1 v1 plus m2 v2 is equal to m1 v prime of 1, right? And the ball here is 1. I guess I should be labeling, in this case, 1 and 2. For the other ones, it doesn't matter because they can be whatever. But yeah, so that is, and you could build this equation like in any manner. So there's like other ways to reshape this, but this is the fundamental conservation of momentum thing. Sum of the initial momentum is equal to the sum of the final momentum. So when we have any forces that are non-impulsive, we don't think about them during the analysis, right? So if we're now analyzing a system and there's a non-impulsive force, so that would be weight, spring, and friction force. Those are non-impulsive. So if we have like this, and the block is moving this way, and we want its momentum, and there's friction, right? Well, that doesn't matter, because the friction has no effect on they won't cause impulse, so it won't be part of our impulse equation, which is this equation here. It won't be part of this equation because friction doesn't cause an impulse, right? So, yeah. That's all there is for this chapter, chapter 9, impulse and momentum. Key takeaways from this is we're using time. We're using a time base compared to work and energy, which use a distance base, right? We still have force and velocity. Those are still pieces of the thing, but we're using time instead of distance, which we can see here with impulse. So, and there's conservation of momentum. This is always applied. There's always going to be conservation of momentum. Like even if there's external forces, it's still conservation of momentum, right? So yeah, keep this part in mind. These are like some example scenarios. There can be more scenarios, like 3 bodies, but yeah, that doesn't matter. There's like some interesting questions that come from 2 bodies that stick together. Like there's like bullet goes this way while block stands still here. Like this is bullet, and then they hit each other, and then now bullet plus block moves find this angle theta that block offsets. That's like an example question of something you could get, right? Remember, you can have velocities that are equal to 0. So like, if you had that they collided and stuck together, but their velocity is 0, right? You would just have that these two things are equal to each other. But that's like unnecessary ramblings. So this is chapter 9, impulse and momentum. Yeah. So thank you for watching. Hope you learned something, and bye.